Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The 1950 publication of Statistical Mechanics by Joseph Edward Mayer and Maria Goeppert Mayer represents a watershed moment in the development of 20th century physical chemistry and theoretical physics. Emerging a decade after their initial 1940 edition, this work consolidated and refined a powerful theoretical apparatus for understanding the macroscopic properties of matter from the bedrock of its microscopic constituents. It champions a specific, powerful viewpoint, the supreme utility of the Gibbsian ensemble method, particularly the grand canonical ensemble, as the most direct and fruitful path to a quantitative theory of real, interacting systems. This essay will conduct a profound evaluation of the book's internal claims, proceeding systematically through its major theoretical sections. The analysis will focus directly on the arguments, methodologies, and conceptual frameworks presented by the Mayers, assessing the logical coherence and physical insight of their monumental contribution to the field. The objective is to dissect the intellectual machinery of the book itself, revealing how its claims constructed a new and enduring paradigm for the study of condensed matter and imperfect gases. Section 1: Establishment of the Gibbsian Framework. The foundational chapters of the Mayer's treatise make a powerful and deliberate claim regarding methodological supremacy. They construct their entire theoretical edifice upon the ensemble concept articulated by Josiah Willard Gibbs. The authors dedicate substantial effort to developing the microcanonical, canonical, and grand canonical ensembles, presenting each as a logical consequence of statistical reasoning about large systems. Their central argument, however, is that the grand canonical ensemble offers the most elegant and computationally powerful framework for problems in chemical physics. The claim is substantiated through its direct mathematical linkage to thermodynamic quantities of immense practical interest. The Mayers demonstrate with meticulous care that the logarithm of the grand partition function, which they denote with the Greek letters I, is directly proportional to the product of the system's pressure and volume, divided by the product of the Boltzmann constant and the absolute temperature. This relationship, expressed as pressure times volume equals the Boltzmann constant times temperature times the natural logarithm of the grand partition function, becomes the central engine of the book. The evaluation of their claim rests on the effectiveness of this formulation. By choosing an ensemble where both energy and particle number are allowed to fluctuate, the Mayers construct a mathematical object, the grand partition function, that circumvents the difficult combinatorial constraints of fixing particle number, a notorious difficulty in the canonical ensemble when dealing with interacting systems. Their argument is persuasive because it recasts a difficult problem of counting constrained configurations into a more tractable problem of calculating a generating function. The evidence they present is the subsequent ease with which they derive the entire suite of thermodynamic state functions directly from derivatives of this single quantity, the grand partition function. The conceptual framework is thus one of profound analytical convenience, claiming that the physically intuitive picture of a small system in equilibrium with a vast reservoir of heat and particles provides the most potent mathematical starting point for theory. The internal logic is impeccable. They establish the problem, introduce the tool, and demonstrate its comprehensive power for generating all relevant thermodynamic information, thereby validating their initial methodological choice as both sound and strategically brilliant. Section 2: The treatment of perfect systems. Following the establishment of their core apparatus, the Mayers applied to systems of independent, non-interacting particles, covering the ideal gas and the Einstein and Debye models of a crystal. The primary claim within these sections is one of validation and pedagogical preparation. The authors demonstrate that their chosen grand canonical formalism flawlessly reproduces the well-established, experimentally verified results for these simpler systems. For the monatomic ideal gas, the derivation of the Second tetrode equation for the entropy proceeds with a clean, satisfying logic. They first calculate the single particle partition function, incorporating the quantum mechanical volume of phase space, Planck's constant cubed. Then, using the properties of the grand partition function for non-interacting particles, they assemble the total function and, through the thermodynamic connections established earlier, arrive at the celebrated equation for entropy. The evaluation of this section centers on its clarity and purpose. The methodology, while perhaps seeming overwrought for such a simple problem, is the key. The claim is that this method, proven effective on familiar ground, is the same one they will deploy for the far more challenging problems to come. The logical coherence is therefore aimed at building the reader's confidence in the universality of the grand canonical approach. Similarly, the treatment of crystalline solids, wherein they derive the heat capacity expressions of Einstein and Debye, serves the same purpose. They model the crystal as a collection of independent, harmonic oscillators and show how the canonical partition function for the system yields the known temperature dependencies of the solid's thermal properties. Their argument is that the statistical mechanical framework is not merely a tool for gases but a universal theory of matter in equilibrium. The evidence provided is the exact recovery of cornerstone results of early 20th century physics. In assessing this part of the work, one recognizes its strategic brilliance. It functions as a crucial bridge, assuring an audience steeped in the successes of the old quantum theory that this new, more abstract Gibbsian formalism is a safe and reliable vessel, fully capable of carrying them toward the uncharted territories of interacting systems. Section 3. The theory of imperfect gases and cluster expansions. This portion of the book contains the Mayor's most original and influential contribution, a theory of real gases built upon a systematic mathematical technique known as the cluster expansion. The central and revolutionary claim is that the equation of state for a gas of interacting particles can be rigorously expressed as an infinite power series in the particle density or activity. The coefficients of this series, the virial coefficients, are themselves calculable from the fundamental intermolecular potential. To substantiate this claim, the Mayors introduce a brilliant mathematical device, the Mayer F function. This function, defined for a pair of particles I and j as f sub h equals the exponential of the negative pair potential u sub h divided by the product of the Boltzmann constant and temperature, all minus 1, possesses the convenient property of being non-zero only when particles are close enough to interact. The entire configuration integral, the core difficulty in the partition function, is then expanded in terms of these f functions. The genius of the argument lies in the subsequent regrouping of terms. The Mayors demonstrate that the resulting complex summation can be reorganized graphically and mathematically into a series of so-called cluster integrals. The first non-trivial term involves an integral over a single f function corresponding to the interaction of two particles. The next term involves a more complex integral over products of f functions corresponding to connected clusters of three particles, and so on. The claim is that the pressure of the gas can be written as a series whose terms are directly related to these irreducible cluster integrals, which they label with the Greek letter beta. Specifically, the second virial coefficient, B2, is shown to be proportional to the irreducible cluster integral beta1, which quantifies two-body interactions. The third virial coefficient, B3, is related to beta2, which quantifies irreducible three-body interactions. The evaluation of this framework reveals its immense power. It provides a direct, causal link between the microscopic forces between molecules and the macroscopic, measurable deviations from ideal gas behavior. The evidence for their claim is the derivation itself, a tour de force of statistical mechanics that, while intricate, is logically sound at every step. The methodology created a research program measure the virial coefficients experimentally, and one gains direct insight into the nature of intermolecular forces. Conversely, propose a model for the intermolecular potential, and one can calculate the equation of state from first principles. This section's claim is perhaps the most profound in the entire book, as it transforms the intractable problem of man-body interactions into a systematic, perturbative scheme. It provided, for the first time, a solid theoretical foundation for the empirical virial equation of state that had been known for decades, grounding it firmly in the principles of molecular physics. Section 4. The application to condensation phenomena. Building directly upon the success of the cluster expansion, the Mayers advance a bold claim about the nature of phase transitions, specifically the condensation of a gas into a liquid. Their theory posits the phenomenon of condensation is intrinsically linked to the mathematical behavior of the virial series they derived. The core of the argument is that the radius of convergence of the power series expansion of pressure in terms of activity is finite. At a certain value of the activity, the series must diverge. The Mayers identify this first singularity encountered on the positive real axis of the activity variable as the precise mathematical signature of the onset of condensation. This is a remarkable assertion, translating a dramatic physical transformation, the appearance of a liquid phase, into a subtle analytical property of an infinite mathematical series. The evaluation of this claim requires careful consideration of its strengths and limitations as understood at the time. The framework provides a beautiful and compelling picture as the gas becomes denser. The contributions of larger and larger clusters of molecules become more significant, until at a critical point, an infinitely large cluster, the liquid phase, can form, causing the mathematical series to break down. The logic is appealing, connecting the physical aggregation of molecules to the mathematical summation of cluster integrals. The evidence they provide is qualitative and theoretical, showing that such a singularity is an expected feature of their formalism. They argue that below a certain critical temperature, the cluster integrals will conspire to produce this limiting point, while above the critical temperature, the series will converge for all positive values of the activity, indicating the absence of a distinct phase transition. The claim was profoundly influential, as it suggested that a theory of the gas phase alone, if pursued with sufficient mathematical rigor, contained within it the seeds of the liquid phase. It framed the problem of phase transitions in a language that theoretical physicists could begin to tackle systematically, while later work, notably by Li and Yang a few years after the book's publication, would provide a more rigorous and complete theorem relating phase transitions to the zeros of the grand partition function in the complex plane. The Mayers' work laid the essential conceptual groundwork. Their claim, that condensation is a singularity, was fundamentally correct and directed the entire field toward analyzing the non-analytic behavior of thermodynamic functions. Section 5. Integration of quantum mechanical principles. The final major theoretical section of statistical mechanics addresses the profound implications of quantum theory, a domain where Maria Goeppert Mayer's expertise as a theoretical physicist shines with particular brilliance. The central claim of these chapters is that the Gibbsian ensemble formalism, particularly their favoured grand canonical ensemble, provides a unified and powerful framework for handling the statistical properties of both classical and quantum systems. The argument proceeds by showing that the fundamental change required by quantum mechanics is a modification in the way distinct microscopic states are counted for systems of identical particles. Quantum mechanics demands that wave functions be either symmetric under particle exchange for particles known as bosons, or antisymmetric under exchange for particles known as fermions. The Mayers demonstrate how this principle of indistinguishability is incorporated directly into the structure of the partition function. Their derivation of the Bose-Einstein and Fermi-Dirac distribution laws from the grand canonical partition function is a model of pedagogical elegance. They claim that these famous distributions, which form the basis of our understanding of phenomena like blackbody radiation and the behaviour of electrons in metals, are natural outcomes of their general formalism when the correct quantum counting rules are applied. The evaluation of this claim highlights the universality and adaptability of their chosen approach. The evidence is the derivation itself. by summing over all possible occupation numbers for each single particle energy level if the constraint of at most one particle per state for fermions and no such constraint for bosons. They derive the characteristic forms for the average occupation number in each case. The framework successfully explains the Pauli exclusion principle's role in the Fermi gas, leading to the concept of the Fermi energy and providing a basis for the theory of metals. Likewise, it explains the tendency of bosons to accumulate in the lowest energy state, setting the stage for a discussion of Bose-Einstein condensation. The logical coherence of this section is a testament to the deep synthesis of classical statistical ideas and quantum principles. The Mayer's claim is that quantum mechanics does not overthrow statistical mechanics, it completes it. Their work demonstrates that the conceptual structure of ensembles, partition functions, and their connection to thermodynamics remains robust, requiring only a deeper, quantum-informed understanding of what constitutes a distinct state of the system. In conclusion, Joseph and Maria Goeppert Mayer's Statistical Mechanics stands as a monumental work whose claims fundamentally reshaped the landscape of physical chemistry. The detailed evaluation of its internal arguments reveals a book of immense coherence, rigor, and strategic vision. Its primary claim for the supreme utility of the grand canonical ensemble is validated through its successful application across a vast range of problems, from the simple ideal gas to the complexities of quantum statistics. The book's most enduring and original claim, the development of the cluster expansion theory for imperfect gases, provided a direct and calculable bridge between microscopic molecular reality and macroscopic thermodynamic behavior, a feat that remains a cornerstone of the field. Furthermore, their assertion that phase transitions could be understood as mathematical singularities in the thermodynamic functions, while later refined, correctly identified the essential nature of the problem and set the agenda for decades of research. Finally, the seamless integration of quantum principles demonstrated the profound universality of the Gibbsian statistical approach. Each section of the book builds upon the last, constructing an unassailable argument for a unified, powerful, and predictive theory of matter. The work is more than a textbook, it is a sustained and victorious argument for a particular way of thinking about the physical world, a perspective whose clarity and power continue to instruct and inspire legions of scientists.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.